Hey guys, welcome back to AlgoYogi. We are doing linked list series. Our next problem in the list is remove nodes from linked list. Let's go to the problem on LeetCode. So it says you're given the head of a linked list. Remove every node which has a value, which has a node with a greater value anywhere to the right of it. Return the head of the modified linked list. So basically, given this list, let me change the view over here. So what the problem is actually asking us, we have this list with us, and we need to remove any node in the list which has a value which is lesser than of the value that is to its right. So basically, if you see 5, we have removed 5 from our final list. Why? Because 13 is greater than 5, 8 is greater than 5. Then 2 is removed because 13 is greater than 5. And it doesn't matter, we don't need to do the multiple comparisons. It's just we need to remove the element only even if there is one value that's greater to the current node. So since it's a list, we will have to, in order to remove these nodes, we will have to traverse the entire list and check if I am seeing any value that's greater than the value that I have already seen. And then I have to go back and remove those nodes from the list. So I think in this case, it makes perfect sense. So basically what we are trying to make it a monotonic list that is strictly decreasing, since that's what it's asking us. This is what we are returning, and we know if it is asking us to remove any node that has a value lesser than any node that is going to occur in the list later. So in order to achieve that, what we are going to do is have a stack. This is the first approach, guys. So there is another approach where we will not use any extra space. Here we will use a big of n time complexity. This is the first approach, and I will tell you guys the approach and also write the solution. So first approach, that is, take a stack, start traversing your linked list. I see a value, I put in the value, then I see another value, and because my stack was empty, so I don't care about the comparison. I see 2 right now, so 2 also goes in because 2 is smaller than 5, so it still goes in. 2, then I come to 13, and then I see that 13 is greater than 2. If my current value is greater than my top of my stack, that means I'm gonna keep removing until this condition is true. So I'm gonna remove 2, I'm gonna remove 5, and anything. Then I put in 13. So this is all done. So I'm just gonna get rid of this. Should remove. Okay, not removing. Anyway, then I'm gonna traverse to 3. Then I check, is 3 greater than 13? It's not. So what I'll do is I'll put in 3. See, the value, I will keep putting values in my stack, but I will check if that value is greater than my top of my stack. If that's the case, then I pop out from my stack, because I want to keep the values only if they're greater than if the value is greater than the values that are about to occur, because I want to have the max value in basically in the front of the list, and it needs to become decreasing, right? Monotonically decreasing. So 3 is basically not greater than 13, then 13 is a valid value. It's going to remain over here. Top of my stack becomes here. Then I get rid of this finally, and then this is visited. I come to 8, and then I'm gonna basically check if 8 is greater than my top of my stack. Yes, it is. So what I do, I'm just gonna simply remove this, and then I'm also gonna keep checking if 13 is greater than 8. That's not. So I'm just gonna put in 8 over here. Then I'm basically done traversing my list. So what I'll do is I'll take this stack and start traversing from 8, or maybe I'll just reverse this stack. And this is an array. Come on, guys. So I will basically start traversing from the end of the stack and make this a list, convert it into a list, and then return the head. So this is what I will return. This is big of n time complexity and big of n space complexity. That's because I have to traverse all the values, and in worst case I'm storing all of them together, and also finally I'm creating a new list, and then I'm returning that list. So let's write this solution down, and or maybe should I, okay, you know what, let's write the solution down and then come back to our second approach. So I'm gonna just change the view here, and then we'll come back to our approach, a cleaner approach, and where we would not use that extra space and just do this playing with the pointers. All right, so let's do that. So as I said, we're gonna have a stack, and then I'm gonna traverse, and let me have a current pointer. Current would be pointing to head, and while current exists, then what I'm doing is I want to append my current value to the stack, right? So what I'll be doing is stack.append and cur.value. So I'm just doing the value, not the nodes. Now this is what I'm doing, and at the same time I will be cur equals to cur.next. All right, that's simple. I'm just creating the linked list and storing the values into my stack, but we know I have to check if my stack exists, it's not empty, and my stack current value, my top of my stack, is smaller than my current value. So if it is smaller than, or maybe we could say equal to, yes, if it is equal to, then also we remove, since we it's all about like keeping the, it says with a greater value anywhere to the right of it. All right, so I'm gonna have equal to sign, and then what I'll do is check my current dot val. So if this is the case, then I need to take the value out of the stack. So I will just basically stack dot pop, and I don't care where that value is going, and that's it. Finally, this will be giving me a stack which will be basically all these values that are need to be returned. But first let's reverse that. So I'm just gonna say stack equals to I'm gonna reverse it, so stack -1. That's like an easy way of doing it. So I'm just gonna call a dummy pointer and list node, or like that, list node. Let's give it a value 0, and that's it. Then I'm gonna start a for loop for I in for, let me just say for value in stack dummy dot next equals to list node, and then I'm gonna give that value, and I'm gonna increment dummy. All right, so dummy, I shouldn't have actually done that. I wanna have the current pointer. So let me call it cur equals to dummy, and I wanna play around with the cur so that finally I can return dummy. Dummy is for not dummy, dummy.next, right? So cur equals to cur.next. That's how we have been doing things. Return dummy.next. So then I'm actually returning the header node, this list 0, and I think that should be it. Let's zoom out, try to submit it. One of the things that I'm not sure about is keeping this, since they haven't shown us if the values are equal to and they could be kept. I think they can be kept, so I'm not gonna have it equal to sign. So let's run it, and it's returning 8 and 13. Although it should have returned 13 and 8. Is it because I reversed it? Oh my god, okay. Because okay. I didn't need to reverse it because it's already, the array is already reversed because I'm appending the values from the back. Oh my god, okay. Right, this should be good. Submitted, and I think, unless it's asking for, okay, it's not very efficient, but it's accepted. So I guess this could be passed as a solution. But now we are going to do a better approach. And what is that better approach? Let me change the view here. Okay. The better approach is, guys, using pointers. But how? All right. This is what we are going to do. So, at the end of the day, what we are actually doing is we are checking from left that I am only going to consider the values which are greater than my current value. If, let's say, if I were to start at the last node, then all the valid node would be the nodes that are max 2, whose values are greater than my current max value. So at this place, my current max value is 8. That's my max. Then I'm seeing, is 3 greater than 8? No, don't consider it. Just cross it off. Is 13 greater than 8? Yes. Then what do? Then I point my pointer to 13. Then I also need to update my max because my current max is 13 now. And then I'm going to check these values. They don't qualify, so I will just return 8. And now 8 points to 13, and that is okay, never mind. This is not what we're going to return. We will reverse this list and then return, because even in the beginning, how we're going to process this list is we're going to reverse it, because that's how we can traverse it better. So we're going to have this list and start traversing from 8, and then keep checking, and also update max, current max currently is 8. All right, so current is 8. Then I check 3 is not greater than 8, so I'm not gonna take it. 13 is, so I'll point its next over here. Then 2 is not, but also I'll make sure at 13 I'm updating this, and then this does not qualify, and this also does not qualify. So what I'll do, this is my final list that remains. This is my final list, 8 pointing to 13. I will not return this, I will return the reverse of this list, because this is the reversed order, and I reversed my list so that I can process those nodes efficiently so that I can, traversing from the back and only keeping the values which are greater than current max, at the same time updating the max from back. So I will reverse this, and this is what I will finally return. That's it. And we're going to have a helper reverse function to do this, and we already know, we have already done a problem that's called reverse linked list, and that's what we will do. We will write a helper function called reverse linked list, not the list. I'm sorry, this is my fourth problem that I'm recording, so my tongue is slipping, but anyway. Okay, I'm gonna comment this solution out. It's a good solution, running solution. Not the best, but a good solution. Okay, so I'm gonna call it brute force, although it's got accepted pretty good. Brute force. Sometimes brute force solution can be accepted as well, but that's not what I was trying to say. I was trying to say it takes big of space complexity, and we don't want that. Here we're gonna remove it. So I'm gonna have a reverse list which takes head, and then I'm gonna have prev equals to pointing to none, dot like that, none. Remember how we were doing it, and current points to head, and you can refer back to the solution where we wrote a reversed linked list. So while current pointer, I want to do is have a pointer next pointing to cur.next, so that I have the next pointer's reference. Then what I want to do is cur.next points to prev. Prev is moved to my current, and my current is looped over, or like maybe jumped over to the next that we saved earlier from the cur.next. Not like that, cur.next. And then finally we return prev, because that's the valid pointer that returns the end of the list, but now its entire list is reversed, and that's what we return. All right, so that's a good function. We're gonna make use of it, and how we're gonna make use? Oh my god, why is it so towards this? I'm sorry if you were having problem watching this. Anyway, I didn't see it how it was being recorded. All right, so what do we do now? Now we're gonna start traversing from let's reverse our list. So I'm gonna say my head is basically use this function and send in head. All right, now my head is reversed. I'm gonna start traversing, so I'll just call it cur equals to head, and then I'm gonna start traversing the current. How I do is while cur, now it's not the current value that I have to deal with, I have to deal with current, but I have to check if my next value are also, remember we will have cur max. Cur max initially would be head dot value, right? All right, so I want to basically check if cur.next exist. You know why? Because that's the value I want to check, because current will always be valid. My current will always be valid. Where I'm starting will always be valid, because that's the first node, that's the first value. That it doesn't have to be greater than anything, because it might be at the end of the list, and it's a decreasing list of values. So I could be anything. I could be negative infinity, doesn't matter. So if cur.next dot value is smaller than my curmax, where is my if? I'm sorry. If this is the case, then what I want to do is cur.next equals to cur.next. Right? I'm skipping that. Otherwise I want to increment my current equals to cur.next. And is there anything else I'm missing? Yes, I have to update in this scenario. Here I don't have to, because that value was already smaller, the current value, next value. So I skipped that. I don't have to current max. I don't have to update my current max, but sorry, I have to update it over here. Current max equals to maximum of current max, comma, cur dot value. All right, because I've already moved it to cur.next. All right, and then finally I am just at a point where I have the list, but it's reversed. So I'm gonna just return not this, reverse list head, reverse the head. So I'll return this. All right, and is there anything I'm missing? I hope not. And if I am, then I'm stupid. Okay, let's run it. Let me zoom out first. I'm gonna run this. Wow, first go and awesome. Honestly, this is the beauty of linked list problems. If you keep doing those, it's like they're so simple. They're honestly so simple. I think graph, dynamic, they're pretty hard, like, at least the recursion one. But linked list, like, they're just so, like, once you get the logic, once they start making sense in your head, where's the pointer is going, okay, I gotta reverse it, I have to point back to somewhere if you're removing nodes and blah blah blah. But if they start making sense to you, it's just about writing this clean instructions, pointing here and there, and voila, they just run in one go. Anyway, writing down the time complexity, and that is big of n. And then space complexity would be, and that is, this is coming from traversing the entire list to reverse, and also, space complexity, where it is down to constant. All right, let's go back to AlgoYogi. Mark this problem also solved. We are making a great progress, and see you guys in the next problem. Until then, bye bye.